Today I'm going to talk about two topics on diversity of eruption style of silicic magmas. I'm going to talk mostly about the critical condition for eruption collapse. Second topic, transition from non-explosive to explosive eruption, is a kind of ongoing work. But I want to introduce the preliminary result on this subject because it might be relevant to the present program of MERS in mantle to some extent. And the first topic is the ground collapse condition. And during explosive eruption, eruption cloud become buoyant plume like this, or pyrogas flow like this, according as it is positively or negatively buoyant. And so the first topic is concerned with the condition that separates these two eruption styles. And then most important physics that separate these two eruption styles is density change of the mixture of ejected materials and air. This diagram shows, horizontal axis shows some mass fraction of ejected material. Ejected material is a kind of mixture of hot particles and volcanic gas. And this shows a mixing ratio between air and ejected material. And when particles are fine enough for the particle motion and temperature difference between particles and gas phases to be ignored, then the mixture it can be treated as a pseudo gas with the equation of state like this. And then this vertical axis shows mixture density normalized by atmospheric density. And density of ejected materials is usually several times greater than the atmospheric density. But as it enters ambient air, then air is expanded by heat. And then the density decreases as air is entrained, and it can be buoyant as the fraction of air increases, and then mass fraction of ejected materials becomes less than 80% and so on.
And this curve is for one particular temperature.
Actually, this not temperature different between them, and the pressure is basically normalized by this atmospheric density. So this can be this is true a wide range of pressures. And is that a correct answer?
The first
temperature is very low here. Air is almost normal temperature, and this is very high temperatures. And the mixing, and then the entrained air is heated up by magmatic magma, then they expand, and then a mixture density become lower than the atmosphere. That is, and then this can be another universal relationship for a wide range of pressure.
But I haven't understood what you're keeping constant.
Are
you keeping the
entropy
entropy of the system constant? Are you keeping the temperature?
And also, pressure is equivalent to these two have same pressure.
Yeah, same pressure. No, that I've understood. But what are you keeping the temperature constant or the entropy constant as you mix?
Entropy constant. So
Entropy.
Energy should be conserved. Yeah, right. And then okay. Let me see. Okay, so actually this is a very important physics behind the phenomenon, and almost the only physics behind it. And then, but in geological context, what we are interested in is the condition that separates these two eruption style in the geologically meaningful parameter spaces like magmatic property, temperature, and water content, and geological conditions like shape of craters and depth of magma chamber and pressure of magma chamber and so forth. And then what is most important is we call magma discharge rate from viewpoint of volcanology. This is very important quantities. This is mass of erupted magma per unit time. And this is a kind of very important quantity which characterizes the intensive volcanoes. So we want to know what is the critical magma discharge rate that separate these two conditions and so on.
Sorry, what's the A?
So I will explain everything because this is very important because it's very, very much complicated. Subscript A means that the quantities after decompression and or compression, and then this mixture reaches pressure equilibrated with atmospheric pressure. All those quantities are denoted by subscript A. Now, I will explain later on. T is actually quantity at the top of crater, and B is the quantities at the base of crater. So that is the meaning of subscript. So at first, so we are interested in the quantities after decompression, and then we want to know critical magma discharge rate and so on. And actually, there are several attempts to understand the critical magma discharge rate for eruption from collapse. Kaminsky and Japan and Karatsu et al. Show that for variable water content, there's a kind of critical magma discharge rate above which buoyant plume is no longer stable and becomes pyroclastic flow like this. And this solid circle means pyroclastic flow, and this open circle shows buoyant plumes, observations.
And the line is some.
A line is model prediction based on one-dimensional eruption from dynamics.
And the data points are from various
observations. So because we can get mass of erupted materials and duration and so on, and water contents from meteorology. But if you look at these results carefully, then there's some exception. For example, St. Helens example is obviously deviated from this line or model prediction. And another exception is Pinatubo case. Actually, pyroclastic flow occurs as magma discharge rate decreased. So there are several exceptions, and then and actually these two examples is the most recent example, and the quantitative data is available. So we have to take these exceptions seriously. And in fact, this model prediction is based on one assumption that exit velocity is always Mach 2. That is a very important assumption. Actually, that is not correct. We will show that is not correct. And then that is why they can draw this line, but without that kind of assumption, we cannot draw this kind of line. And then Woods and Bauer, 1995, already suggested that that kind of importance of exit velocity. And when crater is present at the top of conduit, then because of the decompression or compression inside and above crater, the exit velocity modified to considerable extent. And because of that effect, column collapse condition changed. And in addition to collapse of supersonic flow of Mach 2, they suggested that there must be another type of collapse of subsonic flow like this. So in a way, those exceptions I showed can be explained by this idea, but at present, this diagram rather, I have to say, it's a bit schematic. We don't know scales and so on. So I'm not complaining about it, but I just want to quantify this diagram. Right, that is the first target. And then to quantify that diagram, we have to solve at least these problems. One is eruption gram dynamics to obtain relationship between magma discharge rate and VA. So VA means velocity at pressure equal atmospheric pressure after decompression and compression at the time of column collapse condition. This is the first problem. And as I said, this velocity VA is pressure at the top of crater is different from atmospheric pressure. This VA is of course different from the velocity up here. So in order to get this VA, we have to solve, estimate VA as a function of K, pressure ratio at the crater top, and MT is Mach number at the crater top, or the crater shape 80 over AB, ratio of cross-sectional area, and crater base, and so forth. And let's start with this first problem. So as I said, this subscript is very important, so to distinguish all these quantities. And let's start with the relationship between magma discharge rate and VA, the velocity after the compression and compression. And this relationship can be obtained by one steady model for pressure balance eruption clamp, which was established by Woods 1988. And this model is composed of mass conservation and momentum conservation and energy conservation, and the equation of state for control volume of turbulent fluids, like this. And there's one important assumption called entrainment hypothesis. That is, entrained air velocity is proportional to average velocity. That is a very important assumption.
And L, what's capital L?
L is characteristic radius of the plume. So I will show now how this is valid maybe later on. And the result, this is very well studied model, and the result is something like this. This is height and density and velocity. And as I said, at the exit, density is several times greater than the atmospheric density. That means eruption cloud has initial negative buoyancy, but at the same time, it has initial momentum upwards, and then that is why eruption cloud can rise in spite of negative buoyancy. And then, as it rises, then it entrains air, and the air expands and density decreases. And then before initial momentum, it loses initial momentum. If this can be buoyant, then they can form a stable eruption clamp. But if it loses initial momentum before it gets less than it gets buoyant, then eruption clamps occur. So from this physics, we can tell that the critical condition of eruption clamp collapse is determined by a competing effect of initial momentum and initial negative buoyancy. So that effect can be expressed by so-called Richardson number. And then after some calculations, we can get some critical Richardson number in this form, in which the effect of mixing is taken into account K, entrainment coefficient, and critical mass fraction of ejected material at the time density of eruption cloud is equal to ambient air. And using this critical Richardson number and the definition of magma discharge rate, we can get a very simple relationship between velocity at the time of after decompression and compression and magma discharge rate, like this. And then, so if you give, for example, magma discharge rate something like this, then the velocity below this line become make buoyant plume unstable, and then pyroclastic flow occurs. And then for given velocity, as the magma discharge rate increases and then beyond this line, then buoyant plume become unstable and pyroclastic flow and so on.
Sorry, maybe I missed it. Have you explained why it's the Richardson number that ought to be the...
Richardson number.
So, but why is that the prime parameter?
This is because if you look at this has initial negative buoyancy here,
Yeah.
and then so it's basically it's heavier than the atmosphere.
Yeah.
But if initial momentum is large enough, then it can rise. And before this eruption cloud lose initial momentum, if the cloud can get air, so enough to become buoyant, then eruption cloud become buoyant. So it's a competition between.
I understand that physics, but I don't understand how that necessarily leads to a Richardson number.
So this is actually so you understand competition between the negative buoyancy and.
No, I understand the physics of how.
It's because it's controlling the height at which the fountain rises, because it's like an inverse Froude number. And as the fountain goes higher, it'll entrain more, so it can become buoyant.
So
No, that I understand, but I don't understand what's the Richardson number that's relevant.
Well, it's like the inverse Froude number. So the height of rise of the fountain depends on the Froude number of the fountain. It's like the initial, it's the competition between the initial momentum and the initial buoyancy. So it's
Sorry?
afterwards, she said. I will explain, but actually, anyway, I'd like to say that this expressed a competition between initial momentum and, as Andy said, if the initial momentum is very large, then it can rise against negative buoyancy. So they have a good chance to get enter the air, and it can be buoyant. So it's, and then the answer, another way of answer is it works very much. And this line is based on this very simple relationship. And this black curve is based on a 1D model, so numerical calculation. It's very much consistent with each other. So although there might be some kind of debate, but actually, as far as I remember, in this Uzi course, there's some kind of very simplified calculation, and that support this kind of relationship too. So then, at least we need some. We may need some explanation, but this relationship works very well. So I will use this. All right, and then so we get now the relationship between Q and VA at the time of prime collapse condition. But as I said, the pressure here, crater top, is different from atmospheric pressure. So we have to estimate VA, the velocity after decompression or compression, as a function of K, PT over PA, and the Mach number, VT over sound velocity. So let's think about this problem. And when pressure of at the top crater top is different from atmospheric pressure, then the flow inside the atmosphere is very complex like this, characterized by shock wave and compression wave and expansion wave and so on. And then this flow is far from uniform, but integrating these quantities, mass flux and momentum flux and volume flux, then we can define quantities equivalent to those in 1D top hat model, like this. So we can construct 1D model using these quantities. And then this is also done by Andy and Bauer. So 1D model for decompression and compression just above the crater. The problem is how the average velocity after decompression or compression for given pressure ratio, PT over PA and MT, VT over Mach number at the crater depth. That is a problem. And then we use Mach number instead of velocity from now. And using mass conservation and momentum conservation, we'll get very simple relationship between Mach number here, and Mach number crater top and pressure ratio like this. And I will check this relationship too by 3D simulation too. And it worked again. So the next problem is what determines the Mach number at the crater top and the pressure ratio at the crater top, like here. And then those quantities, in order to get those quantities, we have to solve flow inside a crater. So flow from here. If you give cross-sectional area ratio, AT over AB, and then QB, and we will get pressure at crater top and Mach number at crater top. So that will be next problem to be solved. Right? Then this flow can be described by a very simple flow inside the crater. And then this is mass conservation, moment conservation equation state. And then this is a very classical problem of aerodynamic. And although in geophysical situation like volcano, the effect of gravity becomes quite important. And we can solve this equation by integrating those equations. And from mass conservation, we get the relationship like this. And from momentum conservation, we get a bit busy relationship like this. And this Vg is gas volume, and large VL is volume of liquid part, and this Q star is mass flow rate of standard state, and LSC is a kind of scale height of compressible magma gas mixture.
What is N? Little n?
N.
Little n.
Little n. N is water content in magma. So about 3% or 5%. And because of this small amount value, actually the sound velocity and so on is very dependent on water content. N is, and this is a kind of scale height. And this is, actually this part gives sound velocity. Well, and in this, it is quite busy.
I'm not quite happy yet, because the sound velocity must very strongly depend on the amount of solid material.
Yeah.
Where does that come in?
It is coming as a small number of n. So 1 minus n is give us
N includes the effect of the heat content of the solid material.
Yeah. But heat content is actually, yeah, of course, because this gives mass fraction. And if you multiply temperature and mass fraction, then that will give heat content of my own.
So N includes the solid material as well as the water.
Well, N is the gas mass fraction of the mixture, so 1 minus N is the solid fraction. So that effect is included in N. And the important thing is that volume of, so the mixture, most of volume is composed of gas, but most of mass is composed of solid. That is a very important part. And the volume of mixture is very small compared with gas, so that is why we can drop off this term. And that makes this relationship very simple, like this. Introducing x and y, x is a kind of normalized cross-sectional area, and y is normalized mass flow rate, like this. And then the effect of gravity is taken into account by this normalizing factors. And if we introduce this x and y, then we can calculate xy can be calculated from a Mach number at the top of crater and the pressure ratio at the top of crater. So this ratio relates this x1 and y and Mach number and the pressure ratio. And then, so that means from the point of geology, that means if we know the shape of crater and the mass flow rate at the base of crater, then we can calculate Mach number and pressure ratio at the top of crater by inversely solving these equations. And then once we get K pressure ratio and Mach number at the top of crater, then as I already showed, we can calculate Mach number after decompression and or compression. So we can solve everything from this quantity here to quantity after decompression. Then the result can be summarized like this. This horizontal axis is x, normalized ratio of cross-sectional area, and y is normalized mass flow rate. And then if you, for example, fix mass flow rate at the bottom of crater, then as cross-sectional area increase is very small, then actually flow is choked at the top of crater. So Mach number is automatically 1 at the top of crater, and the pressure is usually higher than atmospheric pressure. And as cross-sectional area, ratio of cross-sectional area increase, then flow is choked at the base of crater, and then still, but flow is under-expanded, so exit pressure is greater than atmospheric pressure. And if the angle is a little bit wider, then flow becomes correctly expanded, and the pressure is just coincide with atmospheric pressure. And if angle is a bit larger than the critical point, then flow becomes over-expanded, and the pressure becomes less than the atmospheric pressure. And if angle becomes farther wider, then shock wave formed inside the crater, and the flow exits as a subsonic flow, something like this. So velocity change in the space of x and y, and this is the Mach number after decompression or compression. And as asked by Harvard, Mach number 2 throughout the parameter space is wrong. Actually, that change according to this parameter space. And then, the Mach number drastically changed in the range of over-expanded this part from low Mach number to very high Mach number.
It's a little bit difficult for me to interpret this three-dimensional graph, especially when the axis sort of goes to 0 there. What's the minimum value of the Mach number?
Minimum value is 0.1 or 2 or something like that. 0 is a bit strange because velocity is 0. Yeah. So this is just because of my skill of renewable.
So it's about 0.1.
Yeah, about 1. Actually, 0.2 of it at the lowest, as far as this parameter range, 0.2 or 0.3. And then this is, the maximum value is not over 4, it's about 3 point something. The maximum value is reaches for the case of correctly expanded cases, some here, as the Mach number become as large as 3. And it is true that there's a kind of plateau shape around Mach 2, but it's not very constant value. And the important thing is there was drastic change in, as I said, this overexpanded region. And then this is actually because because of presence of normal shock here, and that decelerate the flow above the crater. And the shape of this shock and then the velocity change drastically there. So now combining this relationship and this simplified relationship between magma discharge rate and velocity at atmospheric pressure, and then we can get the boundary between buoyant plume and pervious flow in this parameter space of a normalized cross-sectional area ratio and normalized mass flow rate. So, for example, if you give magma discharge rate 10 to the 10th here, then we can calculate the critical velocity using this diagram. From the contour of that velocity, we can draw the boundary of the buoyant plume and the pervious flow, like this. And as you change your magma discharge rate, then the velocity at the atmospheric pressure change, and then the contour will change and the boundary will change, something like this. And from these results, eventually we get kind of scaling law for Coulomb-Collapse condition in the space of x and y, and then this is normalized dimensionless critical magma discharge rate, above which buoyant plume is no longer stable and pervious flow, and below this surface, buoyant plume becomes stable.
Can you just go back to the previous slide just for a second? I'm
Yeah.
sorry. You've got this curve here,
Yeah.
and you've got buoyant plume on this side, pyroclastic flume on the other. What happens inside?
Inside this, this line,
Yeah, what is it the buoyant plume or pyroclastic flow? What happens there?
buoyant plume is,
Yeah. And what if you move to the right?
yeah,
What's there?
this is buoyant plume. So above this curve, buoyant plume, and then below this curve, pervious flow for magma discharge rate 10 to the 10th.
Okay. No, I understand.
Yeah, and this is 10 to 9, and so because that boundary change with magma discharge rate, that gives some kind of surface like this. So actually, all the fluid dynamical effect is taken into account this diagram. So what we should do is verify or justify this surface using 3D simulations. That is what I did. And this is 3D simulations of magma discharge rate of 10 to the 9th kilogram, as some here. And each dot represents 3D simulations. And then the results agree quite well with each other. And this red one is buoyant plume, and black one is pervious flow, and blue one is partial collapse. I will show later on. And this is oscillation. But boundary is very consistent with 3D simulation. And as you see, this surface, then as the magma discharge rate increase, and then the region of buoyant plume reduced to considerable extent, and that is also consistent with 3D simulations. As the magma discharge rate increase, the buoyant plume region decrease like this. So let's go back to this example and look at the result of 3D simulations here and here and here, and we'll see how it's like. And then this is the result of buoyant plume. And actually, what surprised me was the flow is not self-similar at all. It's quite far from self-similar, but the result of 3D simulation is quite consistent with 1D model.
And the colors mean what?
Color means mass fraction of erupted material. So red is almost 100% ejected material, and this is diluted, it's become blue.
And the vent is right at the bottom.
Sorry?
The vent is right at the bottom?
Vent is here.
Yeah.
And then as overexpanded pressure and the Mach number is controlled here, and then partial collapse is something like this. So it is basically most of the part is buoyant and rising, but if you look at this carefully, and then you can see downflow along the column. And then if further overexpanded, then the fountain itself is collapsed and become particles flow fast and mix with air and become buoyant flow, generate a buoyant ash current. And the transitional state depends on the condition, and it sometimes shows a very interesting oscillation like this. So we may be able to explain some of the variation in geological field observation. And then, now, we get this scaling law, and then actually this kind of scaling will allow us to revisit previous collapse condition. Like, if we take the ratio of y and x, that will give known parameter and product of known parameter, and this RT is crater size, radius of crater at the top of crater. And then this ratio gives a line here, and this tells that this is constant crater size, and above which, for example, if magma discharge rate is 10 to the 10th, then above which, that means if crater size is small enough, then eruption plume is always buoyant. But if the crater size is greater than this, eruption cloud become always pyroclastic flow, and between this range, the eruption cloud is conditionally stable, and then depending on shape of crater. And for different magma discharge rate, we get a different range of crater size. And finally, we get the quantified version of Woods and Bar like this. So as this shows the range of crater size, conditionally, eruption cloud is conditionally stable, and this part is always pyroclastic flow, and this part is always buoyant flow, and so on. So at first, I have to say, that this result is really impressive and captures physics. And in addition, we could add some quantification like this. And then, because this is the all dimensionless parameter, so all the effects include this scaling law. And then particularly, effect of magma property T and N is included this sound velocity here. Sound velocity is given by square root of nRT. So if motor content decrease, then this part of value of sound velocity change, and then the boundary of this in dimensional form enlarged or reduced like this. So that is the previous column collapse condition, and it is based on the assumption of Maha 2. But actually, because this is a new result. And then there was an exception like this, but this exception can be quite easily understood because if you consider the effect of additional parameter of RT, because this diagram is a kind of projection of 3D parameter space, and then this region is not buoyant plume, but actually from this we can say that this region should be buoyant plume or paribus flow. So we can explain this exception too. So we could get the scaling law of collapse condition, and we could resolve some problem in previous collapse condition. But it is not the end of the story, because in order to our ultimate goal is to predict changing eruption style from geophysical observation, like ground deformation and so on, which is related to pressure change in magma chamber. And then, in order to get the mass flow rate from the crater base as a function of chamber pressure, we have to solve another problem, flow in a conduit here. But this program has contain many contentious programs. I can't discuss everything right now here. So I just give a preliminary result, which is related to second topic's transition from non-explosive explosive eruption. I have only 5 minutes. It's okay.
Oh no, we've got at least 15 minutes. Yeah.
So I'm just going to the second topic. And then, as I said, the conduit flow model gives a relationship between chamber pressure and mass flow rate like this. But this relationship between chamber pressure and mass flow rate is very complex because of multi-phase flow effect. And sometimes have this kind of nonlinear relationship. And for example, if we think about the magma chamber surrounded by elastic rock like this, then magma is supplied from deeper part by Q in. Then pressure increase, and then as pressure increases, then magma flow is derived like this. But if within the range of positive differential resistance, then basically the Q out eruptive mass flow rate is controlled by magma supply. But as this Q in go into the range of negative differential resistance, then very rapid change from low flow rate to large flow rate can occur. That might explain the transition from non-explosive to explosive eruption. So that is the second topic. Then this is the controlling, the governing equation, which looks very busy, but maybe many people are already familiar with this equation because this is quite similar to the equation of actually melting mantle. So this is mass conservation of volatile and non-volatile like this, and the momentum conservation of gas and liquid, and this is constituted by equation for deformation of matrix magma, and this is the equation of state, and then this is crystal growth, and unlike the case of melting mantle, actually gas is given as a function of pressure, so it's not constant. And then to think about volcanological problem, we take the effect of gas escape, that conduit is leaky, and gas can escape from through conduit wall. That is taken into account here. And another thing is inside conduit, a crystal can grow with a rate which is proportional to the rate degree of supersaturation like this. So they are very similar to migration in mantle, but slightly different. And then this part is can be rewritten as like this. So this describes the permeable gas flow through magma following Dancy's law. And this equation expresses, this is the buoyancy effect between gas and liquid phase, and this is mechanical interaction between gas and liquid. And this gives a kind of approximation for viscous effect of wall from wall, volcanic conduit wall. And this describes the resistance of compaction. And we think that these equations can give some clue of and for understanding of transition from non-explosive to explosive eruption. And so far, we recognize two important features in these equations. One is in the case of lava dome magma flow, compaction of silicic magma is strongly controlled by very large viscous wall friction near the surface. And this is the viscosity, crystal and liquid mixture as a function of pressure. And because of crystallization here, then as the pressure decreases and the crystallization occurs, and the viscosity increases drastically near the surface. And that causes the very big viscous wall friction. So liquid flow is strongly suppressed by because of this viscous wall friction, but gas is kept flowing because it is light. That is why strong compaction occurs here. And actually, we observe very low porosity lava room, but it might be explained by this compaction effect. Another important effect is there's two feedback mechanisms causing negative differential resistance. And one is viscosity change due to crystallization like this. As I said, the viscosity of magma increases as it reaches near surface. But if mass flow rate increase, then the degree of crystallization decrease because of delay of crystallization. That reduces wall friction, and that causes increase in mass flow rate. So this gives one positive feedback. Another positive feedback is related to gas escape, density change due to gas escape. And this magma flow have resistance of due to gravitational load. And if mass flow rate increase, then gas escape through the conduit walls is reduced. And then volume fraction inside the conduit increase, then gravitational load decrease and the mass flow rate increase again. This is the second type of positive feedback. And then this mechanism is proposed by Melpnick and Sparks, and then we propose actually this mechanism would be very important. So far, we haven't succeeded in solve all these equations because of numerical difficulty, but we just dropped this time and solved one pressure model. Then our preliminary result on one pressure model is already quite interesting. This is the result. And this solid curve is relationship between mass flow rate and chamber pressure for steady solution. And then this dotted curve and dashed curve is a kind of this relationship for very extreme case. So all the gas is escaped. And this one is, there's no lateral gas escape here. So usually this relationship for this solid line. And we gave magma supply somewhere here. This has a negative differential resistance. So steady state is not stable. Then small perturbation grow and then small perturbation grows and the mass flow rate increase drastically like this. And then during this transition, porosity, this is depth and porosity, increase quite rapidly. So through this situation, basically all the gases escape from conduit wall, but the high porosity part propagate from deeper part to shallow part, and this part become gas volume fraction becomes more than 0.8. That means transition to explosive eruption. And then the efficiency of lateral gas escape decreases like this, and overpressure change like this. So this is just a preliminary result, but we think that the effect of positive feedback of gas escape might play a role to transition from this dome form eruption to very explosive eruption like this. So this is our conclusion. So I talked about two topics about related to diversity of eruption style. One is ground collapse condition, and that condition can be accounted with simple scaling law obtained by 1D 3D model. And that scaling law for the ground collapse condition is confirmed by 3D simulations. And previously proposed ground collapse condition can be regarded as projection of the present ground collapse condition to a part of bounded space. The second topic is transition from non-explosive to explosive eruption is strongly controlled by gas escape from conduit flow. And then I expect that accumulation of idea and the knowledge of melt in mantles can be applied to the problem, gas in magma. Thank you very much.
Thank you very much, Tak. Questions?
Is the last thing you talked about the same effect as happens in geysers?
In what?
Geysers,
Geysers.
geysers, where essentially the density of the column is reduced by boiling.
Yeah.
And so the thing goes woof.
Yeah, yeah. I think in the case of geyser, right?
You call them geysers. I don't know whether they should be geysers or geysers.
Yeah. Geyser. Okay, geyser.
You did got
Yes.
lads.
Neither of us are right.
Anyway,
It may depend on which country you come from.
I think so.
in Japan,
Geyser is the word, it's an Icelandic word.
Oh, is
So
it?
it's geyser.
Wait, so
Pronunciation.
that is the correct thing.
Yeah, I can tell you, you did it right.
geyser.
So there.
In Japan, guys. Anyway, that guy, geyser is controlled by phase transition. Maybe the boiling is very important. It's the pressure change and boiling change, and that change of the density, and that causes that kind of repeated phenomenon. But in the case of, so I think the features are very similar, but maybe detail of physics is quite different.
Oh, yeah,
And in order to predict the transition, we have to understand that kind of detail.
Well, there's a solid fraction and porosity here, which the thing word beginning with G doesn't have.
Geyser.
That's a little bit too simple. Because
If you say, what does it say?
because of the fact that, I mean, you know, the volume fraction of the gas, right, is essentially the same problem as here. I mean, here it's coming out of solution, and there it just boils.
But this is
When that
controlled
shows
by-
the porosity,
The porosity is controlled by basically the degree of gas escape rather than dissolution. So in the case of geyser, the phase transition from liquid water to steam is very important, right?
Yeah.
And then if that is so this
And then-
porosity change is controlled by dissolution, maybe there must be some kind of similarity. But in the case of the flow rate and rate of gas escape competition control the porosity.
I understand that, but where is your gas coming from?
From magma,
So it's ex-solution of magma.
exsolution magma.
And in the geyser, it's coming from the boiling of the water.
Yeah,
so there's a thermodynamic difference as well.
You lose heat in both cases. It comes out of solution, it's going to cool it, and when it boils, it cools it. I think there's more similarity. I think what the major difference is that your volume of magma is typically very, very much greater than in a geyser.
mm-hmm.
That how do you know how big they are? I mean,
The
simply from the amount
radius
of
is
water that
about
comes
several
out.
tens of meter.
What?
The radius of conduit is maybe several tens meter.
And the volume at the bottom.
This the bottom is quite large, say it's sometimes kilometer and sometimes hundreds of meters. So this is and there may be another important difference. Would be the length is quite large. This is kilometer, and that gives large effect of gravity. So if we look at carefully, then which term is very important in each equation, that might be different from between two phenomena.
Bob, I think, is not. Bob's
No,
not
okay.
What they saw in the eruption in Iceland was that they could actually see the decompression propagate downwards
Yeah.
through the column,
It's
through the magma column.
Yeah.
Yeah.
Yeah, that is actually I expected first. So before I solving this one, I say this is preliminary because at first I thought that there must be kind of porosity wave comes from top to down because we observed that there was kind of eruption, Vulcanian type eruption, and the fragmentation surface propagate downwards. So that is what I expect here, but actually, so far we get the porosity wave from deeper level to upper level. So I feel that there must be different type of physics behind it. So that is what I want to distinguish from it. So I have no answer, but I realize that problem.
Solving the full equations helped there?
Pardon?
You said that you couldn't solve the full equations.
Yeah, you
Yeah,
neglected
actually-
the compaction stress term.
Yeah, actually, if we have time, I want to ask this problem. And then, sorry.
So you said there was a numerical difficulty with including the compaction.
Yeah, this is comes from this term. Oops, sorry. This term has the second order differential.
Yeah.
And then this gives a very small compaction length.
Yeah,
Is-
you've got to
which
resolve the
is
boundary layers.
much smaller than length of concrete. So if we try to find the solution that satisfies the top and bottom of boundary condition, you have to be very carefully choose this part and this part. Actually, you have to do some kind of calculation from the top and then matching without a one pressure model and then maybe do some boundary condition, something like this. Then I haven't succeeded in that. But so if you have a good idea, I want to solve this because
Because you need that term to describe solitary waves and things, don't you? So, yeah. Maybe you have to artificially increase that compaction length so you can have something you can resolve.
But this problem has a difference because you've always got this Mach number in all these problems, which you don't have in the mantle.
But basically, this equation, as far as dome-forming eruption, dome-explosive eruption is concerned, the Mach number is very low, and then the low,
I see, so
lower is
you're
not.
ignoring it.
And
Well, then it should be. Yeah.
Going back to the first part of the talk.
Yeah.
I mean, volcanoes must have a whole series of different crater shapes.
Yeah.
And some of them won't be symmetric. And so there's presumably a whole envelope of different conditions for that collapse, depending on the specific geometry of the craters.
the geometry of elongated and so on, or
Well, Medicine Helens, it kind of, it was asymmetric. I mean, there was a back of
Yeah,
the
yeah.
crater, not the front. And so there was there'd be an asymmetric pressure force driving the flow in a particular direction.
yeah, yeah.
So, I can see this is axisymmetric, and but in fact, in practice, comparing it to real field data,
Yeah,
actually thinking about the specific shape of the crater is going to be very important in actually getting the specific conditions.
Well, it's not only the crater, the contour.
Yeah,
but crater is also important.
but the shock, the formation of the shock wave and so on will be very different if you.
So I absolutely I agree with your opinion, and then so the comparison between observation and the model is should be affected that kind of things very much. I agree with you. Yeah, but yeah, well, this is just a kind of framework of it.
Are there observations you could use? Sorry to go back to the second half.
Yep.
Are there observations you could use at dome-forming volcanoes to support the model, like related to the gas flux?
Well, actually, only we could compare, say, a porosity of lava, and then and sometimes we can get a transition mass flow rate if we get the radius of the conduit and then mass flow rate. Then we can tell the transition state of this. And then for the moment, we can just say that the kind of maximum value of dome eruption is rather consistent with this model, but that is all for now. So there's no very quantitative comparison between observation and this idea.
Last questions? In which case, can we just thank TAC once again, and there's tea over in the Newton Institute if anyone wants to come up for tea.